So we're comparing real numbers. We need to define what real numbers are. Okay. Real numbers differ from complex numbers, or sometimes they're called imaginary numbers. And imaginary numbers actually have a real definition. They're not just like 11 or something like that. Just make up numbers. Yeah, you never heard of like little kids count and make up weird numbers? 2011. That was a year, but it's not a number. Already got Bilbo's birthday, his 111st birthday. Yeah. It's my 111st birthday! That's not his voice, though, but it might as well be. So we're going to look at real numbers. And we can break real numbers into two different categories. Rational numbers and irrational numbers. Rational numbers are any number that you can express as the ratio of two integers. Now, an integer is a whole number, or a negative whole number. And so a rational number is a ratio, or can be written as a ratio of two integers. What does ratio remind us of? What are ratios? Starts with an F. Fractions. Okay? So rational numbers can be expressed as fractions of integers. If they're written as a decimal, the decimal either has to have a repeating pattern or it has to terminate. That means it has to end, like 0.75 ends at 0.75. Or you could have negative 0.33333 and just have threes forever and ever and ever. So integers are rational numbers because you can write any integer as a fraction over 1. Like negative 4 is the same as negative 4 over 1. Negative 2 is the same as negative 2 over 1. 57 is the same as 57 over 1. So those are also rational numbers. That's why we have the integers grouped inside the rational numbers. They're part of the rational numbers. They're what we call a subset. And then we have a subset of the integers called the whole numbers, which are basically all of the positive integers plus 0. So the whole numbers are subsets of the integers are subsets of the rational numbers, and the rational numbers are subset of the real numbers. So if it's a whole number, it's also an integer, it's also a rational number, it's also a real number. Every whole number is an integer, a rational number, and a real number, but the same doesn't work in reverse. Not every rational number is an integer. Not every integer is a whole number. Now the other half of the real numbers, and half I use as a loose term because it's not like it's, half of the numbers are irrational. It's just the other part of the set is irrational. Irrational numbers are numbers that can't be written as a fraction of two integers. For instance, the square root of 2 can't be written as a fraction of two integers. It's a decimal answer that doesn't repeat the same pattern over and over again. Any square root of a number that is not a perfect square is going to be irrational. Pi is irrational. It's also irrational how much pie I can eat. It's very irrational. In Algebra 2, you're going to learn about the number e. He couldn't have said that right. Yes, the number e. It's approximately 2.78128 and so on. It's also irrational. Don't need to know that now, but it's another number, kind of like pi. So we're going to take some time to classify numbers. We have to decide whether it's a real number, a rational number, an irrational number, an integer, or a whole number. Now you can look at these like boxes. If I place something inside the whole number box, it's also inside the integer box. It's also inside the rational box. It's also inside the real number box. But just because it's in the rational number box doesn't mean it's in the whole number box. Make sense? You got boxes within boxes. Okay? Now the real number box is divided into two parts, and there's no crossover between them. Okay? There's no number that's both irrational and rational. So once you determine that a number is irrational, it can't be any of the numbers that, or any of the types of numbers that are rational. Can't be any of those if it's irrational. Let's look at the first example. Radical 24. Now we've got a radical here, so the first thing we should consider is 24 a perfect square? Is there some whole number that when we square it, we get 24? No. That means it's what kind of number? Irrational. And because it's irrational, it can't be a whole number, it can't be an integer, it can't be a rational number. But it's still what kind of number if it's irrational? It's still a real number. The next one, radical 100. Is 100 a perfect square? Yes, so what's the square root of 100 equal to? 10. Is 10 a whole number? Yes. So once we know that it's a whole number, we know that it has to be in every box that contains whole numbers. So that means it's also what? It's also an integer because the whole numbers are inside the integer box. If it's an integer, what else is it? There's a smaller box, rational. And then the rationals are in what bigger box? Real. Everybody good so far? Next one is the opposite of radical 81. Is 81 a perfect square? Yes. So what's the opposite of radical 81?
Negative 81.
No. You got to do the radical 81 first.
9.
Okay, so what's the opposite of radical 81?
Negative 9.
Negative 9. Is negative 9 a whole number?
No.
No. Is it an integer?
Yes.
Yes, which means it's in every box that contains the integers. So what else is it if it's an integer? Rational. And if it's rational, what else is it? Real number. Everybody good so far? Questions yet? All right, now once we know what type of numbers we're looking at, we want to be able to put them in order and graph them on a number line. Really, we want to be able to put them in order, but graphing them on a number line sometimes helps. So let's take a look. We have a list of numbers. 4/3. Negative radical 5. Radical 13. Negative 2.5. Radical 9. Now, let me be very clear. When they ask you to put these in order, you need to put them in order using the numbers that they give you. But we might want to find decimal approximations or different expressions that represent what they are. For instance, what's radical 9 equal to? 3. But when I give my answer, I need to write radical 9, not 3. Okay? I'm just going to use the fact that it's 3 to help me put it in order. But my final answer should have a radical 9 in it. What's radical 13 approximately? Let's see. 13 is between two perfect squares. What perfect squares is it between? It's got to be between radical 9. So radical 13 has got to be between radical 9 and radical 16, which means radical 13 is somewhere between 3 and 4. And which number is it closer to?
4.
4, because 13 is closer to 16. Okay? So that's going to help me place it. Okay? Radical 5. Negative radical 5 is got to be between negative radical 4 and negative radical 9. Now, if we think about this, remember that the bigger the number is negative, the smaller it is. Negative 13 is smaller than negative 12, right? So negative radical 9 is smaller than negative radical 5. So negative radical 5 is somewhere between negative 3 and negative 2. Which one's it going to be closer to? Negative 2, because 5 is closer to 4 than it is to 9. And it might help us to know that 4/3. It might help to rewrite that as 1 1/3. So let's plot these on our number line. We'll start with the negative 2.5 should be pretty easy. It's going to be right here. Halfway between -2 and -3. And the radical 9 should be pretty easy because that's equal to 3. So that's got to be there. Where should the 4/3 go? Where should 4/3 go if it's equal to 1 1/3? It's number line, guys. Where does 1 1/3 go? Between 1 and 2, but closer to 1. Okay. 1 1/3 goes here. So 4/3 label right there. All right, negative radical 5 we said is between -2 and -3. What's it closer to? -2. The question is it between -2 and -2.5 or -2.5 and -3? That's what we think. Open up your calculator. Tell me what radical 5 is. 2.236. So it's going to be somewhere in there. Oops, wrong button. So that's where we're going to put our negative radical 5. All right, we need radical 13, which we said is between 3 and 4, but closer to 4. Yep. All right, I've got all 5 numbers on my number line, so now I can see what order they go in from least to greatest. So all I have to do is rewrite them. Starts with -2.5, then negative radical 5, then 4/3, radical 9, and finally radical 13. There's my order from least to greatest. If you're on the number line, it's left to right. That make sense? Any questions? Okay, the last thing we're going to touch on is if-then statements. A conditional statement can be written in if-then form. It starts with a hypothesis, the if, and it's followed by a conclusion, the then. So for instance, if we're given the statement, no fractions are irrational numbers. We want to write this in if-then form. Hypothesis and then conclusion. So hypothesis is what comes first. Are we making a statement about fractions or about irrational numbers? We're making a statement about fractions. We're saying something about fractions. And so our hypothesis should address fractions. So we're going to say if something is a fraction. Now, I need to start with a noun. Don't say if it. Don't start with a pronoun because we need to know what it is referring to. So what should I write if blank is a fraction?
If X.
No, we can be more specific than that. What is a fraction? Something very generic. A noun that describes a fraction. A number. If a number is a fraction. Once we've established that what we're talking about is a number, then we can use it. Then we can use a pronoun. Then it, what's our conclusion?
Is an irrational.
Are we saying is or is not?
It is.
This word right here tells me that they're not. We're saying that fractions are not irrational numbers when we say no fractions are irrational numbers. So we'd say then it is not an irrational number. Is that a true statement? Is that true? Think about it. What's the definition of irrational? If you're not sure, look back to the last page. Okay? Look at all the numbers that are irrational. And on the bottom of page 74, it defines it for you. It says an irrational number is a number that cannot be written as a quotient of two integers. What does quotient mean? Division. What's another way of writing division? A fraction. So if it's an irrational number, it can't be written as a fraction. So if it is a fraction, it can't possibly be irrational. Does that make sense?
Yep.
Let's look at the next statement. All real numbers are rational numbers. So we start with our if. What are we talking about? Real numbers. So what should our hypothesis be? If what? Go ahead, Ryan.
Number.
If a number what? No, what did we say we're talking about? If a number is a real number, we're making a statement about real numbers, so the real number should be in our hypothesis. Then it what? Is rational. We don't have the word no in there, we have the word all, so we're saying that it is a rational number. Now, notice that when we read it in our if-then, we lose the word all, but the word all still applies because we're saying if a number is a real number, that shouldn't be plural. Bad grammar. If a number is a real number, that means all real numbers that we're talking about here, all numbers that are real numbers, are rational numbers. Is that true?
No.
Is that true? Are all real numbers rational numbers? Okay, so if it's not true, we need what's called a counterexample. We need just one number that's a real number, but not a rational number. Somebody give me a number that is a real number that is not a rational number. A number that is a real number, not a rational number. Caleb? Pi. So we would say this is false because we need a number that satisfies the hypothesis. It has to be real. Pi is a real number, so it fits the hypothesis, but not the conclusion. It's not a rational number. We only need one counterexample. When you're proving something false, you need one counterexample. If they say all, you only have to find one that doesn't fit that. Okay. It's like if somebody says, I always share my cookies with you. All you need is one example of one time that they didn't share their cookies with you, and they're a liar. And so you must steal their cookies. Any questions? All right.